This lecture, we continue learning quality management. For quality management, we focus on three things: what, why, and how. And in the former lecture video, the video topic 8 part 1, we have already discussed what and why. We have discussed what quality is, what quality management is, and why the quality management is so important. In this lecture, we will focus on how to manage quality. The first thing of this lecture here, I'd like to review what we have learned in the former lecture, which related to what and why. So in the former lecture, we have discussed the definition of quality. The quality is a term the customer used to describe their satisfaction with service or product. And then we analyze what kinds of dimensions the customer used to express their satisfaction for a product or for a service. So we discussed the 8 quality dimensions of products and the 5 quality dimensions of service. And the next subtopics in the former lecture video, we talked about the principle which called quality at the source. We analyze 3 things of quality at the source: the prevention, the personal responsibility, and the standardization. And then we discuss why aspects of quality management. We discuss the cost of quality, as well as the relationship among those 4 types of cost of quality. The last subtopics we have discussed in the former lecture, we talk about the 2 important philosophies in quality management. One of them is the TQM, which is the total quality management. And this slide shows the 8 core principles of TQM, which proposed by ISO, the International Organization of Standards. And except for the 8 core principles, this is one of the way we analyze, we understand the TQM. And I also provide you another way to illustrate the core principles in TQM, which we focus on the 3 things over there, and we also focus on other principles. And the 3 main principles of TQM are the customer satisfaction, the employee involvement, and the continuous improvement. So this is what we have introduced for TQM. And another important philosophy in quality management is Six Sigma. So we have learned what Six Sigma is, and because the main objective of Six Sigma is to reduce variation. So we also discussed the 2 types of the variation, which are the common cause variation and the special cause variation. The last thing I introduced about Six Sigma, also the last thing I introduced in the former lecture video, is the Six Sigma certification. We have 5 levels of Six Sigma certification. They represent the different abilities to do the Six Sigma project. And the website I pasted here is the information which can help you to learn more about the certification of Six Sigma. So this is what we have learned for the former lecture. In terms of quality management, we talked about the what and the why aspects of quality management. And today's lecture, the topic is quality management part 2. We will focus on the how. the how aspects of quality management. So we will know how to manage quality. And here I will introduce 3 tools, and we will focus on the first two, which are the SPC and the process capability. And the third tool we will learn is the cause and effect analysis. In general, we also call it the fishbone analysis. These 3 tools help us to manage quality while evaluating quality, improving quality. SPC here is a methodology for monitoring the quality of manufacturing or the service delivery processes to help identify and eliminate unwanted causes of variation, while the process capability allows one to predict or to quantitatively how well a process will meet the specification. Briefly, the SPC is to give the manager or give the company the information whether their process is in control and out of control. And when we mention in control and out of control, actually we focus on the special cause variation. And the process capability, they give the manager or the company the information whether their process, even though the process is in control, but whether they satisfy the specification. So the process capability is focused on common cause variation. If you are not familiar with what special cause variation and common cause variation are, please recheck the slides. After the Six Sigma variation reduction, so we have the detailed explanation about what common cause variation is and what special cause variation is. And the last tools, the fishbone, or we call the cause and effect analysis, it is a simple and graphical method for presenting a chain of causes and effects and for sorting out causes and organizing relationships between variables. So this is the 3 tools I will introduce in detailed nature. So the first thing, let's take a look with the SPC, the statistical process control. So we call it the S here represent the statistical, which means we will use some statistical number to evaluate the quality, whether the whole process is in control or out of control. And the main tools we use in SPC we called control charts. The control chart looks like this picture. So it has 3 lines over there, the UCL, the LCL, or the target, or sometimes here stands for the average. So we have UCL represent the upper control limits, while the LCL represents the lower control limits. And the blue line here is the target or the average according to the data you collected. And this control chart is for the M&Ms, and it represents if your target is like each bags of the M&Ms should include 24 blue candy. But if you take a samples and you find like in the sample 1 it's not exactly 24, it is the number around 22 or 23. And in the second bag you checked, it also not in the 24. It's some number around the 25 or 26. So you check all the samples you connect and you put those numbers in the control chart and to see whether the process to pack the M&Ms is in control or not of control or out of control. So this is how a control chart looks like. And then we're back to the general steps of constructing and using the control chart. The first step is preparation. So you need to decide several things. The first thing you need to decide is the matrix. For the M&M's example, we choose the matrix is the number of the blue candy in one bag. And for anything you want to evaluate the quality, you need to choose one metric. For one control chart, it illustrates one metric. So the first thing you need to decide which metric you want to evaluate the quality for this process. It might be the weight of a product, it might be the length, the weight, or the length, or others for a process. So you need to decide the metric to be monitored and controlled. And then another thing you need to decide is about the sample size and the frequency of sampling. So the frequency is about like you want to take the unit or the items every 10 seconds or every 20 seconds or every 2 hours. So you need to decide the frequency. And about the sample size, what is the sample size? When we mention the sample size, you need to figure out the differences between sample size and the number of samples. The number of samples is how many samples you pick up, and the sample size is how many units in a sample. So they are different. So you need to decide the sample size. You want to choose 20 units for a sample, or you want to pick 10 units for a sample. Then you can set up the control chart. This is the preparation step. The second step is the data connection. So you need to start to connect the data you need. You already decide which matrix you want to have. If you want to analyze the weights for a product, so you connect the data for the units you pick up and calculate the relevant statistics for such as the average, or the standard deviation or others, and then plot the statistics on the chart. And the third step is determination of the trail control limits. So if we think back to the examples of M&Ms, so for any control chart, we have 3 lines. The 3 lines is the upper control limits, the lower control limits, and the center line, or we call it the target line. So we have 3 lines. This is the things you need to compute according to the data you collect to have those three lines. So you need to have a center line, which is the target or the average line, and the upper or the lower control limits. And depending on the different types of the control charts, we have the different way to compute these three numbers. And the fourth step is to analyze and interpret your control charts according to what you obtain for the first three steps. So you need to give a conclusion whether the process is in control or out of control, and if necessary, recompute the control limits. The fifth step is to use the charts as a problem-solving tool. So you already have the control chart. If it is out of control, you can you can fix the problem and continue connecting the data, and to put the data into your control chart and to analyze which variation, which causes has the impacts on the variation, and take corrective action. The last step is determination of process capability using the control chart data. So if you take a look this here, this is another tools we use. So if you have already take the correct action and you find the process according to the SPC, the control charts you obtained, your process is in control, then you can continue your analyzing of the quantity while compute this number, the process capability, to say even though the process is in control, but whether it satisfies the specification. So this is the general steps of construction and use of control charts. And before we learn how to compute the control charts and the different types of the control charts, we need to understand one thing about the matrix. So I have mentioned like the step is to preparation, and the first thing in the preparation step you need to determine is the matrix. So you need to determine whether you want to analyze the weights or the length or the colors, or just briefly the number of the defects. So according to the different matrix you pick up, actually we have the two types of the matrix, and according these two types of the matrix, we need to choose the different types of the control chart to evaluate whether this process is in control or out of control. And the first matrix types is what we call the variables, and another is the attributes. What is the variables? This is focuses on the characteristics which can be measured. So what kinds of characteristics can be measured? Just like what I have mentioned. The weight, length, diameters, and others. All the characteristics can be measured, which can be measured are the variable matrix. And what is the attribute? The attribute matrix is the characteristics can be quickly counted. What is it? What is the number which can be counted? So if we mention counted, which means the number you connect, the data you connect are the integer. A traditional or common attribute measurements is the number of defects. So think about these examples. You have 5 samples and you want to pick up 100 units in each sample, which means you have 500 units in total. So for the sample 1, for the 100 units you pick up, you find 20 defects, and you just count. You count there are 20 defects in sample 1, and in sample 2 it has 15. So for the number of the defects, these are the characteristics that can be quickly counted. They are not the characteristics that can be measured. So we have these two types. And another way for you to analyze it is like you can consider the features of the number. So if it is a continuous number, which means 1.1, 1.12, 2.3, which is continuously, those matrices we call the variable measurements. And the discrete matrix, which calculate for the data that are counted, which are the integer like 1, 2, 3, 4, or 100, 101, and so on and so on. They are not continuous in number. Actually, they are the number can be counted, which we call the discrete matrix. So we have these two types. This is the variable, and this is the attribute. So the first step of control chart is you need to determine the matrix, and you need to understand which types of the matrix you determine. And then you can choose the different types of the control chart to measure, to evaluate the quality of the process. For continuous matrix, or for the we call the variable control charts, we have R chart and X bar chart. And for the discrete matrix, which is the attribute control chart, we have P chart and C chart, which means if you choose the weight as the measurements you want to analyze whether the process is in control or out of control, the weights should be the continuous number. So you need to choose R chart or X bar chart to evaluate whether the process is in control. If you have the matrix just like the simple counted number, for example, the number of the defects, how many defects for a sample, then you should choose the P chart and C chart. Okay, so what I have talking in the past 10 minutes is about the types of the matrix. And why I mention the types of matrix, because you need to figure out which types of the matrix for your evaluation of quality. And according to the types of the matrix, you need to choose the different types of the control chart. But in general, we need, for any control chart here, we have 3 lines: the upper control limits, lower control limits, and the center line. So let's take a look with the R chart first. Here are the formula to compute the upper control limits and the lower control limits for R chart. What is R chart? The R here represents the range. For example, you want to evaluate the process of a laptop production. A laptop, and you choose the weight as the matrix you want to evaluate. And you have 5 samples. And for the sample 1, you pick 4 units, so the sample size is 4. And for the sample 1, you have a unit which is weighted 2 pounds, and the second unit weighted 2.5 pounds, and we have 2.75, and we have 3. So this is the 4 units in the sample 1. And what is the range? What is the R chart focuses on? The R chart, we also call it the range chart. So it focuses on whether the range is in control or out of control. So the range for the sample 1 will be the highest number, the maximum number, the 3 minus 2 is 1. So the range for the sample 1 is 1 pound, which means in sample 1, the maximum weight of laptop is 3, and the minimum weight of a laptop is 2. So we know the range in sample 1 is 1. And this is what we focus on for the R chart. And for the upper control limits and the lower control limits, it equal to the D4 times the average of R, and the D3 times the average of R respectively. What is the average of R? The same example here, we have the 5 samples. So for the number 1, we have range as 1 pound. For the sample 2, we have 0.5 range. For sample 3, we have 1 also. For sample 4, we have 2. For sample 5, we have 1. So the range for the sample 1 is 1, the range for sample 2 is 0.5 until the range for sample 5 is 1. The average of several past R value is we sum all the range for all the samples together and divided by the number of the samples. So we have 1 plus 0.5 plus 1 plus 2 plus 1. This is the total ranges for all 5 samples and divided by 5. Then this is the average of R values. This is the R bar, the average of R. And the average of R also, in general, it should be the center line. So we already have 1 line for the R chart. And for the another 2 chart, for the another 2 lines, the upper control limits and lower control limits, except for the average of R, we have the D3 and D4. What are they? The D3 and D4 are the constants that provide us 3 sigma limits. Why we choose 3 sigma limits? So we actually have 2 sigma limits, we have 3 sigma limits, we have 4 sigma, we have 6 sigma. The 3 sigma limits in general is a benchmarking. So when we talk about the CPK, the process capability, we will know that the CP equal to 1 for 3 sigma limits. So we take the 3 sigma limits as a benchmarking. So we consider the control chart under 3 sigma limits, and the D3 and D4 are the constants which follow the 3 sigma limits, which means the D3, D4 are not the number we need to calculate. Actually, this is the number, the stable number according to the sample size. If the sample size is 2, we have a number for D3 and a number for D4. If the sample size is 4, we have another number for D3 and D4. So they are not the number you need to compute. Actually, the number you can find for a table over there. And this table is not only introduce the value of D3 and D4, but also of the A2. So the A2 is for the X bar chart. what is the X bar chart? The X here stands for the average. So if we back to these numbers here, what is the X, the value for X? The value for X is the mean. So for example, for the number 1, the sample 1 here, we have 2, 2.5, 2.75, and 3. We sum them together and divide it by 4 because we have 4 units in total. And then we will have a number over there. This is the X value. And why the X2 bar is the average of the past sample means. I always call it the average of average. So we have the average here. In general, we use a short line above a symbol stands for the average. So we have the average. This is the sample 1 average, and we can calculate the sample 1, the sample 2 average, the sample 3 average, the sample 4 average, the sample 5 average, and we plus those 5 average together. And divided by 5 also. So this is what we called the average of the sample mean, the average of average. And the average of average is what we are looking for the center line. So this is the number of the center line, and another 2 lines, which is the upper limits and the lower limits. It depends on the X2 bar and the R1 bar, R bar, which is the average of the range at A2. So we can compute the X2 bar, the R bar, according to the data we connect. But the A2 is also the constant, which follows the 3 sigma limits, which can be found according to the sample size via this table. So for example, if we have the sample size is 4, then the A2 will be 0.729, the D3 will be 0, and D4 will be 2.282. And you can find the upper and lower limits according to the A2 value and the X bar and the average of range you calculate. So this is how we draw the control chart via the data you collect. So this is the formulas for computing the limits and the center line for control charts for R chart and X bar chart. So now take 1 minute to review what I was talking about. And briefly, we talked about the control chart, and you need to understand the control chart is the tools of the SPC. And the control chart is help manager and to evaluate the quantity, to evaluate whether there is a special cost variation to make the process out of control or not. And we have 4 types of the control chart: R chart, X bar chart, P chart, C chart. And which one you should choose to evaluate the quantity for a process? You need to choose the control chart according to the type of the matrix you pick up, you determined. And for the R chart and X bar chart, they are for the variable matrix, which is the characteristics which can be measured. And here are the formulas to obtain the limits, the 3 main lines of control chart for R chart and X bar chart. The R chart for the upper limit is equals to D4 times average of R. The lower limit is equals to the D3 times the average of R, and the average of R, which means the average of a range for samples. And the D3 and D4 are the constants according to the 3 sigma limits, and we can find the value of D3 and D4 according to the table I provide here. And you also can check this table on your textbook. And the same for the X bar chart. The upper control limit is equals to the X2 bar, which is the average of the sample mean, plus A2 times average of R, and the lower limit equal to the average of the sample means minus the A2 times the average of range, and the A2 just similar to the D3 and the D4. It is a constant according to the 3 sigma limits, and we can find the A2 also according to the table here, according to the sample size, not the number of sample but the sample size. And now let's take a look with the example. The management of West Anise Industries is concerned about the production of a special metal screw used by several of the company's largest customers, and the diameter of the screw is critical to the customers. The table here shows the data for 5 samples, and the sample size is 4. So here is the questions. In this process, in statistical control or out of control? If we want to know whether a process is in control or out of control, we can use control chart to help us. And for this problem, the table shows the diameter. The diameter is a variable metric or an attribute metric. This is the first thing we need to think about before we start to compute the control chart's statistical number, because we need to make sure which control chart we can choose. And because of the diameter actually is the variable measurements, which means the number here, the characteristics can be measured, and the number here is continuously. So we choose the R chart or X bar chart or both of these two charts to evaluate this process. And for R chart and X bar chart, we already have the formulas to compute the limits and the center line. So the first thing we take a look with the R chart. As I have mentioned, the R chart, if we think back to the formulas, the upper control limits for R equal to the D4 times the average of R. The D4 we can find for the table according to the sample size, and the only thing we need to compute is the average of R. In order to have the average of R, we need to have the R for each sample. We have 5 samples here. So for the sample 1, the range, the R should be the maximum minus the minimum. So the maximum is 0.5027 and the minimum is 0.5009. So we use 0.5027 minus 0.5009, and we obtain the range. For the sample 1, we have 0.0018. And the same for the sample 2, we need to find the largest number and we need to find the lowest number because we want to know the range. The largest number is 5041 and the lowest number is 5020, so we have a range with 0.0021 and we can calculate all the ranges for each sample we have, and then we will be able to find the average of a range. So we just use these 5 numbers, we just sum these 5 numbers and divide it by 5 because we have 5, and we will find this is the average of range. So we will have 0.0021 is the average of range for all the 5 samples this company pick up. And according to the numbers we have, then we will be able to find the upper limits and the lower limits. So we have the average of a range, which is 0.0021, and D4, the value of D4 depends on this table, and we know the sample size, which is the number of the units in a sample, is 4. So this is the sample number. We have 5 samples, and in each sample, we have 4 units. So the sample size is 4. And if the sample size is 4, we can find the D4, which is the last column here represents the D4 for different sample size. And the sample size 4, the D4 will be 2.282. And the D3 will be 0. So we're back to the formulas here. So 2.282 times the average of range, which is the upper control limits, and the 0 times 2.0021 is 0, which is the lower control limits. And the center line is the average of range. So we have 0.0021. So this is the average of a range, which is the number of the value of a center line. And according to the data we collect and according to the data we compute, then we will have the R chart for this problem. The R chart here, we just draw the 3 lines, the upper limits, which is 0.00479, and 0 as the low limits, and this is what we have for the center line. So we already have the control charts, and we need to plot the data information for each sample into the control chart. So for the sample 1, if we back to the range, for sample 1, the range is 0.0018. So we plot 0.0018. This is 0.0018 as the point for sample 1. And the same for the sample 2. It should be the point of 0.0021. So we have the 0.0021 for sample 2 and the same for other 3 samples, sample 3, 4, and 5. And then we will have a completed control chart, the R chart. And according to the R chart, we can have the idea that the process is in control because all of the points is within the limits. And we also have like a detailed explanation about whether it is in control or out of control according to the control chart you obtain. So this is the way we can find the R chart, and we'll also be able to use the similar way to find the X-bar chart. But for X-bar chart, we have different formulas to find the limits. So for the upper control limits, we have the x2 bar plus a2 times the average of range, the average of range which we have obtained, the 0.0021. The a2 we can find for the table. So the sample size is 4. So we're back to the table here. The a2, the second column here represents the a2 value. So if the sample size is 4, the a2 should be 0.729. So we have 0.729 here as the a2. But how to calculate the average of average? So we're back to the table. The x2 bar represents the average of sample means. So we need to know the sample mean. For sample mean, for the sample one here, how to obtain the 0.5018? The 0.5018 is the means, the average of these 4 units. So we just use 0.5014 plus 0.5022 plus 0.5009 and plus 0.5027, and we sum them together and plus 4 because we have 4 units in a sample, and then we will be able to obtain 0.5018. This is the average of sample 1. And similar, we can obtain the average for the sample 2, sample 3, and sample 4, and sample 5. Once you have the sample means, then you will be able to find the average of sample means. So we just use those 5 numbers. We sum all the 5 numbers here and divide it by 5 because we have 5 samples. And then you will be able to obtain the x2 bar, which is 0.5027. So we have 0.5027 plus the a2, 0.729 times the average of range. This is what we obtain for the x-bar chart, the upper control limits for the x-bar chart. And we use the x2 bar minus a2 times the average of range. Then we will have the lower control limits for the x-bar chart we have here. And according to the numbers we obtain, the values we obtain, then we can draw the control chart over there. And for the sample 1, because this is the x-bar chart, so we care about the mean of sample, the average of sample. So for the sample 1, the number here, the number to represent in x-bar chart for sample 1 should be 0.5018. So this is the number for sample 1, and this is the number for sample 2, sample 3, sample 5, 4, and sample 5. So we just put the numbers over there, and according to this chart, these figures here, we notice the sample 5 is above the upper control limits. If there is any points, any sample points above the upper limits or below the lower limits, we say that the process is out of control, is not in statistical control. So this is about the R chart and X bar chart. They are for the variable measurements, which means the characteristics can be measured. And another 2 control charts is the P chart and the C chart. So they are for the counted numbers. And before we introduce the P chart and C chart, there is another way to compute the X bar chart. So we have, if you know the standard deviation, which is the sigma here, if the standard deviation is known, we can use another way to compute the upper and lower control limits. And then we move to the P-chart and the C-chart. The way we construct the P-chart and the C-chart are very similar to the R-chart and X-bar chart, but with the different formulas. So for the P-chart, we need to find the first thing is the sigma p. So we need to calculate the standard deviation. And what is the p? Because of the P-bar chart and the C-chart, we focus on the attribute measurements, which is the integer number 1, 2, 3, or 20, 21. So all the integer numbers. So we care about the P here stands for the number you connect. So if you care about the number of defects and you have different numbers of the defects for different samples, then this is the values. And the first thing you need to calculate for P-chart is just like you need to calculate the standard deviation. So you have the standard deviation equal to the average P times 1 minus average P divided by N. N here stands for represent the number, the number of the units. And the P-bar here is the average of the P, which is the average of the data you connect. So this is the center line. And the upper limits and lower control limits equal to the average P plus Z times sigma P, which we obtain for these formulas. And P average P minus sigma Z. And be noticed here the Z. The Z here equal to 3. If you follow a 3 sigma limits, if you follow a 2 sigma limits, Z equal to 2. So it depends on what kinds of sigma the standard deviation limits you use. And in general, we make Z equal to 3 because we follow a 3 sigma limits. So this is how we compute the P-chart. And I also provided you examples and the details about the details process, the computation process. And if you take a look at the examples, actually the values you connect is about the defects, this is the wrong account numbers for this example because this is takes evaluate a back process. And according to the numbers you have, you will be able to find the upper, lower, and the center line. And it didn't, for this slides here, it doesn't show the complete formulas, but if you download the PowerPoint on Canvas, it will show the complete formulas. And then the last control chart I'd like to introduce is about the C chart. The C chart is also talking about the attribute measurements. And C here also stands for the data you connect. So if you care about the wrong account numbers, just like the former example, or if you care about the number of defects, this is the data you have. And it's very easy for any center line of C chart is just the average of the data you connect or the target value, and the upper limits and the lower limits equal to the average of the values you connect plus Z, the same Z equal to 3 or 2. It depends on which standard deviation limits you follow, times the square root of the average of C. and the lower limits is the average of C minus Z times the square root of average of C. And I also provided you another example here and also the detailed computation process. So this is about the control charts. And whether it is in control or out of control, I provided you several examples. The first examples we call the normal. So all the points, all the sample points within the limits, and it spread over the center line. And the wrong one is like we have several successive samples which is close to one side. And the sudden change is just like we have samples changed or not. The one of the sample is very close to the lower, and the another two is just like increase to move to the upper limits. So it's a sudden change. And the exercise control limits, which means we have points above the upper limits or below the lower limits. So this is what we call out of control, and this is the, if you obtain the control chart looks like this, which means you need to take action to find the special cause variation and to fix that. And this table here shows the examples if whether your control chart is out of control. So if a single point falls outside the control limits, which is above the upper or below the lower, all 2 out of 3 successive points are on the same side of the center line and farther than 2 sigma for it, or 4 out of 5 are on the same side, or a run of 8 in a row are on the same side, or any consistent or persistent patterns tells you that your process includes systematic variation. So for the control charts, I also include the examples in the textbook in the funnel in several slides, and you can check both the textbook and the slides to make sure you can do some practice for these examples over there. So this is all the contents I'd like to introduce in terms of the SPC, the control chart. And the next two I'd like to introduce is about the process capability. As I have mentioned, the process capability evaluates whether the process meets the specification or not. And the typical questions that are asked in a process capability study are: where is the process centered? How much variability exists in the process? Is the performance relative to specification acceptable? Or what proportion of output will be expected to meet specification? So this is the typical questions related to process capability. And because we have a design specification, so for the problem we analyze, actually we have a normal value and a tolerance, which is a allowance above or below the nominal value. So which we can regard as the limits, the upper and lower limits. And the process capability equals to the acceptable value divided by the actual value, which means the process capability index, the CP here, is defined as the ratio of the specification within to the natural variation of the process. So it equals to the upper limits minus the upper specification limits minus the lower specification limits, which is the tolerance, divided by 6s. I use s to stand for the standard deviation, but in general we use sigma, so we have 6 sigma or sigma. And the CP, this process capability index, if the values less than 1 here, it means a significant percentage of output, which means the observed variation will not conform to the design specification. When Cp here equal to 1, which means the observed variation is the same as the design specification. And if the values of the Cp exceeding 1 indicate good capability, in fact, many firms require that their suppliers demonstrate a high value of the Cp. So the higher the better, equal at least should be larger or equal to 1. And note that the value of the Cp does not depend on the mean of the process, the average of the process. Thus, a process may be off-center but still show an acceptable value of Cp. So to account for the process centering, we use another measures which called CPK here. In the textbook, it introduces you one of the way to compute the CPK, which equals to the CP times 1 minus K, and K equals to the T minus the mu. Mu is the average of the actual observation, and the T is the target observation, and divided by the upper specification limits minus the lower specification limits divided by 2. So this is one of the way. But actually, because we consider whether it is centered, so we consider the upper specification limits and the lower specification limits. So I provide another way to find the CPK. So we consider the one-side process capability index. So we consider the upper side and the lower side. The upper side capability index equal to the upper specification limits minus mu. Mu is the average divided by 3 sigma. And we use mu, which is the average minus the lower specification limits divided by 3 times mu, that's 3 sigma. And we pick the minimum number for CPU or CPL as the CP key to stands for to represent whether this process is off-center or not. And a high value of CPU here indicates that the process is very capable of meeting the upper specification. So the CP key here is the worst case. The worst case, and provides an indication of whether both the lower and the upper specifications can be met regardless of where the process is centered. And actually this is the value that most managers focus on, the CPK here. In some, the process capability focuses on whether the process meet the design specification, and the CPK here represents whether this process is centered or not. So except for whether it is like satisfy the specification, we sometimes in general we also care about whether it is centered or not. So this is about the things about the process capability analysis. The last two I'd like to introduce is the cause and effect diagram. And because of its structure, it is often called a fishbone diagram. And the cause of effect diagram is shown here. At the end of the horizontal line, the problem is listed, and each branch here porting into the main stem represents a possible cause, and the branches porting to the causes are contributors to those causes. And this diagram also identifies the most likely causes of a problem so that the further data collection and analysis can be carried out. So this is, for this example here, this is the problem. And we have different branches here represent the causes, the machine's causes, environmental causes, methods, materials, people, measurements. And this diagram here helps the manager to find the reasons, to find the causes which cause the effects here, the problems here. And according to the fishbone analysis here, the manager could have an idea about what kinds of data they should collect to improve this quality of this process. So this is the cause and effect analysis. And this is all the contents I'd like to introduce for the topic 8 quality management, the how aspects.